Okay, good evening. So we're going to be looking a little bit about collision theory today. So some of you will have had this lesson today. So there's a lot to get through in this lesson. So I'm putting this up here so you can get a look at the notes again and finish off all of the work from the lesson. So by the end of the lesson we should have learnt about how collision theory can be used to explain rate of reaction and how surface area of solids affects those rates. So in the lesson you might have had a chance to draw our particle diagrams showing how reactions occur and annotating showing our collision and sufficient energy requirements. So these are the two key points that I'll be looking for in exam questions. Written a 100 to 150 word account of the role play which we've done, where you walk around the room and high-fiving each other, modelling the particle collisions. And you should have seen a demonstration of different marble chips in acid of different sizes, showing how surface area increases. The books, the AQA Additional Science is available through Caboodle, Chemistry for You is available in the lab, and obviously I would have done the demonstration in the classroom. Okay, so that's what we're up to this evening. So the notes you hopefully saw during the lesson. We had a conversation about how chemical reactions happened, and hopefully you came up with the ideas that we need some reactants, so something to actually react. The idea that temperature might affect our rate of reaction, how fast the reactions occur. Might have come up with the ideas of catalysts and about particles colliding as well. So our definition of collision theory at GCSE is that for a reaction to occur we must have these two conditions. Particles must first collide with each other and there must be sufficient energy. So if we've got two particles, which we'll just call A and B, so we've got two particles A and B. So particle A here, which we'll just colour in blue, and particle B here, which we'll colour in green. If these two particles are moving around, as all particles do, if one particle is moving in this direction and one particle is moving in that direction, clearly these particles will never collide with each other and therefore reaction can't occur. If, however, the two particles are moving towards each other, like so, then the chances are they will collide and we have the possibility of a reaction where the two particles come into contact with each other and new bonds will form and we form a new compound. So that's our collision theory, the collision aspect. They have to have sufficient energy though. If these are moving too slowly, instead of us forming a new compound with these two joined together, the other possibilities, if it's a low speed collision, is that we just end up with the particles bumping off each other and going back the way they came. So we just go apart. So this one here would be high speed. Okay, so they have to have sufficient energy, a minimum energy, and we give that the name activation energy. So both together give us our definition of collision theory. So if I had time I would have looked at some of these reactions and describing it in terms of collision theory. So what observation would we have seen when magnesium and oxygen were burnt together? Well, the observation which you all know from middle school or primary school is we see a bright white light and then a white powder produced. Explanation in terms of particles, the heat from the Bunsen makes the particles move quickly, and then oxygen and magnesium collide and react, and the product in this case is obviously magnesium oxide, which is the white powder. Magnesium and hydrochloric acid, well, that doesn't require any heat. As soon as you put the magnesium into the hydrochloric acid we will have seen bubbles formed and the magnesium slowly disappearing. So in this case the magnesium particles and acid particles are colliding and reacting, and a salt, magnesium chloride, salt formed, which is soluble, so soluble in water. So that dissolves away, and that's why the magnesium seems to disappear. The calcium carbonate, this is one you will have seen from C1 chemistry when we looked at the limestone cycle. Any carbonate tends to react with acids, producing carbon dioxide. So in this case the bubbles were also formed, and the calcium carbonate disappears, and this is because the acid and carbonate particles collide and the carbonate decomposes, forming carbon dioxide gas. Okay, so that's what disappears, and then obviously we're forming, disappears, it bubbles out of solution and escapes into the atmosphere, and we're obviously producing a gas, a salt and water, so the solid dissolves away. Sodium thiosulfate and hydrochloric acid, well, these are two clear colourless solutions, and we don't really see anything happening straight away, and it looks like there is no reaction, so that's clear and colourless, and that's also clear and colourless. But if we give it 30 seconds or so, we do start to see it turning slowly cloudy, and over the course of a minute or so it goes very cloudy, and we get an opaque solution. So no observed reaction to start. Slowly the solution turns cloudy. You might also have smelt sulphurous smell, at least, and here it's the thiosulfate and acid particles reacting, producing solid sulfur particles. Okay, and because they're a solid forming and they're very small particles, they make the solution go cloudy. So this one we will come back to actually in a future lesson when we're looking at how temperature affects rate of reaction, because this one changes very significantly when we change temperature. So that's a good reaction to look at that. The copper carbonate, we heated that in the Bunsen flame, and this one, it's a green powder, turns black, and it looks like it boils. And that's only because it's a very fine fluid. The powder, the copper carbonate powder, is very fine, and again, in a similar way to the calcium carbonate, when we react with an acid and the carbonate decomposes and it produces carbon dioxide gas, when we heat this carbonate, the copper carbonate, it also decomposes, releasing carbon dioxide gas. And because we've got such a fine powder here, the gas, tiny little gas bubbles come out in it. The powder is fine enough to be moved around by that gas, and so it looks like it's boiling, but it's not. It's just the release of the gas. So explanation in terms of particles, well, really we're just decomposing the copper carbonate, and in fact it's just the carbonate that's decomposing in this case. So you can ask the question of whether collision theory really counts in this case in terms of particles colliding, but we certainly do need the sufficient energy to decompose the carbonate in this case. Okay, so that's a slight anomaly, but that's what makes the science is interesting. It's the anomalies that we need to be able to explain. Okay, so that would be detailed notes from that, if you didn't get time in the lesson to finish those ones off. And obviously pause this if you need to get that all down. What makes the reaction go faster? So we've got three or four things which can make reactions go faster. Increase in temperature, make reactions go faster. That's the one most people know about. If we increase the concentration or pressure, so concentration if we've got solutions, pressure if we've got gases, this makes reactions go faster because we're getting more particles packed together, more chances of collision. And the equivalent for surface area, which we looked at in the lesson, was for solids. We'll come back to all of these, the temperature, concentration and pressure, in future lessons, and catalysts will come to towards the end. But today we looked at surface area, and simply put, and this website here you might want to have a look at. It's got some very good animations for you to have a go at, and little reactions to have a go at. If we take the idea of a nail, and for a reaction to occur, particles have to collide. If you consider an acid particle, for example, trying to react with this nail, and we draw our acid particle here, then the only collisions this acid particle can make will be the ones on the outside of the iron nail. These ones in the middle, the ones shown in white, are protected by the outer ones, and so they can't react. So the reaction is limited to those particles on the outside. If, however, we chop up the nails, then we are exposing more of the inside of it, and we can count up the extra atoms, and we find that there's more yellow atoms compared to the white ones. So we can do this in a bit more detail. And you might have had a go with the multi-cubes, and these are the numbers if you didn't quite get around to it. But if we just take a nice 2D example to illustrate this, then just counting the number of edges available in these boxes, clearly we've got 1, 2, 3 edges down here. That makes 6 across there, 9 down there, and 12 there. So 12 possible places of reaction if each side of the box can react. If we chop this up into smaller blocks, then we're making the inner ones accessible. So we've got the 3 down the outside as before, and we've got the 3 down the outside as before, and the 3 across the bottom, and the 3 across the top. But now we've exposed these inner sides as well, so that's another 3, making us 15, and then 18, 21, and 24. So by chopping it into 3 pieces, we've doubled the number of places on the solid which can react, so we've doubled the rate here. If we carry on chopping up and we count all the sides, then we get to 30 at this stage, and once we've chopped it up into tiny little blocks, we get to 36. So here, just by chopping it up into large pieces, smaller pieces, smaller and smaller, so larger number of particles, we increase the number of places that other particles can react, and therefore we're increasing the rate. So formally, if we look at how surface area affects rate of reaction, the rate of reaction will increase with surface area. As the surface area increases, more particles can be collided with, and therefore the rate of reaction increases. So that links back with our collision theory. Particles must collide, and they must collide with sufficient energy. By providing more particles, we have more collisions, and therefore we have a greater rate of reaction. So the last activity we hopefully had time to do was this modelling. So you are all the particles, and we move around in the room, and every time you pass another particle, you high-five them. So pass another student, you high-five them, and you kept count of how many collisions you had, and then we added them all up. We changed all the different reaction conditions to have a look at how that changes our rate of reaction. And the model data which I'll provide for you is as follows. So if you didn't have a chance to write down the data from today's lesson, you can use this as model data. So our standard start conditions are this one in the middle, so normal temperature, normal pressure, and normal concentration. We had 200 reactions in the 30 seconds. If we then decreased the pressure here, then we had fewer reactions, and if we increased the pressure, we had more reactions. If we decreased the concentration, we had fewer reactions, and we didn't have extra pupils to help out, but if we'd increased the concentration, we would have had 400 here. And we noticed that both concentration and pressure had a similar effect in terms of going up or going down, whereas temperature, when we went to a higher temperature, so you moved around more quickly, we had much higher reaction, going from 200 to 600, whereas when we decreased the temperature, you walk around with little pigeon steps, then the rate of reaction dropped pretty low as well. So the last bit of the lesson was to write this summary of the evidence provided, write the 100 to 150 word account of how the role play activity demonstrates collision theory. So that's the last bit of writing up, and this is probably the homework that I will have set you. So hopefully all these notes will help you with this lesson. As I say, there was a lot to get through, so this is provided to help you finish off. The website that I was showing you earlier is this one, and it's a very good one. So it's called Absorb Learning. If you just Google Absorb Learning, you can see all sorts of different reactions and notes and little tests you can have a go at. So well worth a look. Okay, thanks for watching. See you next time.